The grade reads 22% and the machine is not slowing. Early morning at a Wyoming surface coal mine and 336,000 pounds of Komatsu D575A-3 SD is descending with a full blade. The brakes are fading. The operator had run large dozers for 16 years across 3 states. See, he knew brake fade on a D11. This was different. 336,000 pounds on a 22% grade with no margin left. The D575A-3 SD is the largest production bulldozer ever manufactured. At 152,600 kilograms and 1,150 SAE net horsepower, it operates in a category that no engineering standard had been designed for when it was first conceived. This is the story of the Super Dozer, its origins in a Japanese prototype, its deployment in American mines, and the structural crises those operations produced. The machine was extraordinary. So were the consequences. To understand the D575A, go back to Houston, Texas in the spring of 1981. At the Conexpo equipment exhibition, Komatsu unveiled the D555A, a 1,000 horsepower prototype that exceeded every production bulldozer then on the market. The D575A never entered production. The global recession of the early 1980s crushed demand for capital-scale mining equipment, and Komatsu shelved the prototype. The engineering was retained. Development stalled for nearly a decade. By 1989, the economics of strip mining had shifted. All open-pit coal operations in Appalachia and surface mines across the American West were pushing existing dozer fleets to capacity. Komatsu resumed development with urgency. The successor was designated the D575A-2 Super Ripper. Field testing began in North America in 1989. A full production launched in 1991 at Komatsu's Osaka plant, the first of its kind assembled in series production. The SD configuration arrived in 1995. The first machine went to a coal mine at Cabin Creek, West Virginia, where it immediately doubled the site's production rate from 375 to 750 yards per scheduled operating hour. That production number came from the blade, 11 feet 11 inches tall, 24 feet 3 inches wide, with a rated capacity of 69 cubic meters. What a Caterpillar D9 would need 12 to 15 passes to equal. The engine was the Komatsu SA12V170E, 12 cylinders, 4-stroke, turbocharged, and aftercooled. At 1,150 SAE net horsepower and 1,800 RPM, it produced more power than any crawler dozer engine that had preceded it in serial production. In 2001, Komatsu released the D575A-3 SD, a redesigned machine with revised frame sections, updated powertrain electronics, and reinforced undercarriage components. It weighed 152,600 kilograms. It was headed for the large-scale surface mines of the American West. If you want to see how the D575A-3 SD was pushed past the structural tolerance of its own track frame and what it took to keep it running in the mines of the American West, here's what I ask. See that subscribe button? It's our exchange, your way of saying this reached you. Hit subscribe if this resonated, drop a like if it moved you, and tell us in the comments what you know about the Super Dozer. It helps us share more stories like this. Back to the machine. The D575A-3 SD moved across the open-pit bench on a route its operators learned through thousands of hours of repetition. A fixed dozing path measured not in feet, but in tons of material moved per shift. Each push cycle began at the crest of the bench. The blade dropped, the machine advanced, and 69 cubic meters of overburden moved ahead of 24 feet of steel. Cycle times ran approximately 6 minutes from cut to return. But the Wyoming benches were not flat. An uneven ground placed asymmetric bending loads on the track frame, the fabricated steel member connecting each crawler assembly to the main chassis. At this weight, those stresses were severe. The track frame was the structural spine of the machine. During blade loading on uneven terrain, our bending forces at its weld joints approached the material's design tolerance. Komatsu had engineered to the limit. The mechanical evolution of bulldozers, history's most punishing projects, and the technical details no one else covers, That's what lives in the membership section. Join, and you get full access to 20-plus minute deep dives built for people like you. Now back to the D575A-3 SD. Track frame cracking was documented in D575A operations during the early 2000s. Whilst the failure mode was specific, fatigue cracks forming at weld toes along the crawler box bracing. Inspection intervals were compressed to catch propagation before it advanced. Weld repairs on a 152,600 kilogram machine were not roadside operations. Each repair required a certified weld technician, preheat procedures on plate steel thick enough that cold temperature welding would introduce new failure points. The cycle, run, inspect, repair, run, became routine at the highest production D575A sites. Operators knew which sections of their bench were hardest on the frame. They adjusted approach angles to reduce asymmetric loading where the ground allowed. The undercarriage demanded the same discipline. Track shoes on a D575A were far heavier than comparable D11 components. Shown on abrasive rock benches in Nevada where rates consume track components at fractions of their rated service life. Replacing the track assembly required specialized tooling and a crew of at least 6. The machine had to be detracked on-site using hydraulic equipment transported separately. The scheduled track service was a major logistical event. At one Nevada surface mine, a maintenance supervisor developed a track rotation protocol, shifting active shoe positions before wear reached critical limits. The protocol extended service intervals by approximately 20% at that site. Yes, the hydraulic circuit ran up to 1,258 liters per minute at operating pressure. Hose failure under load was a serious injury risk. Safety protocols required visual hydraulic inspection every 4 hours during production shifts. Moving the D575A between job sites was itself an engineering challenge. The machine had to be disassembled into component form, 6 to 8 truckloads, depending on local transportation regulations and road weight limits. The blade alone required a dedicated lowboy trailer. The track assemblies, mainframe, engine package, and cab traveled on separate loads. A relocation that took a D11 crew one day took a D575A crew several days to execute. The operators who ran the D575A were selected carefully. Standard surface miner certification was not sufficient. Sites required candidates with high production dozing experience and specific training in the D575A's ECMV controlled transmission and steering systems. The Palm Command Control System put all primary functions at the operator's fingertips. On a 152-ton machine, idle input lag meant blade position error at production speed. Experienced operators learned to anticipate momentum, not react to it. Night operations required careful management. Blade visibility from the cab was limited by the 11-foot blade height. Operators relied on grade monitors, depth gauges, and ground feel, the vibration signature of different substrates through the seat. At full production load, the D575A-3 SD consumed approximately 120 liters of diesel per hour. A 10-hour shift burned roughly 1,200 liters per machine. At 2 machine operations, us fuel trucks ran to the bench on a 4-hour cycle. Operator shift transitions required a full machine walk down. Blade clearance, track tension, hydraulic lines, cab interior, and mirror positioning. The procedure took 20 minutes. At high production sites, that time was built into the schedule. In Nevada's high desert, temperatures swung from below freezing at pre-dawn startup to over 100 degrees by midday. The cooling system was sized for worst-case heat. Cold weather startups required preheat cycles before any load was applied. Though the Wyoming coal operations pushed the machine on different terms, wetter substrate during spring thaw, haul routes carved into hillsides where bench grades exceeded 20%. These were the conditions that stressed the braking system hardest. If these stories mean something to you, take a look at the thanks button below this video. It's a small gesture, but it's the most direct way to say you want more of this. Let's continue with the D575A-3 SD. The D575A-3 SD used ECMV-controlled steering clutches and brakes, electronically modulated for precision. On a 25% grade with a full blade load, the braking energy exceeded what any production dozer had been designed to dissipate. Brake fade events were recorded at high-grade Wyoming benches in the early 2000s. Descent rate exceeded what standard controls could hold. The emergency field procedure: drive the blade into the bench face and use the steel as an anchor. The blade anchor technique was a field adaptation, not factory specified, but developed and shared informally between mine operators. It worked. It also placed extreme sudden load on the blade frame and hydraulic tilt cylinders. Mine engineers at Wyoming operations subsequently modified the slope descent protocol. Maximum blade load on grades above 18% was reduced by operational rule. Pre-shift grade surveys were added to D575A assigned bench safety plans. These were not design failures in the conventional sense. They were revelations of what happens at the absolute upper boundary of production scale steel. As every structural limit the D575A encountered was exactly where the engineers had calculated it would be. Between 1991 and 2012, approximately 53 D575A machines were built across all model configurations. Now, the A3 series ended at just 12 units, 11 built between 2001 and 2007, and one final custom order completed for Alcoa in Australia in 2012. The 2008 financial crisis ended demand at this scale. Between 2007 and 2011, no new D575A orders were placed. The manufacturing jigs at Komatsu's Osaka plant sat idle while the machines already in the field kept running. In North America, 31 D575A machines were sold from new. The majority worked Appalachian coal fields, with others deployed in western surface mining operations. They remain among the rarest production bulldozers ever put to work on American soil. Komatsu discontinued the model after years without new orders. Manufacturing resources, jigs, molds, and precision tooling were retired. The physical record of how to build the world's largest production bulldozer was decommissioned. The era ended quietly. Machines in the field kept working. Some remain operational today, maintained by crews managing an aging parts supply. Keeping a D575A running now resembles historic aircraft maintenance as much as it does conventional dozer service. The Caterpillar D11, the D575A's nearest competitor, continues in active production and development today. The Super Dozer exceeded it in every dimension of raw scale. It could not compete on the economics that sustain a broader serviceable fleet. Operators who ran the D575A remember its presence in the pit. 16 feet tall, 38 feet long. Moving 69 cubic meters per pass on a bench no other machine could match. Nothing since has replaced it at that scale. The engineering problem Komatsu solved between 1981 and 2001, how to build a production crawler dozer at twice the operating weight of any predecessor, remains one of the most demanding achievements in construction equipment history. The D575A defines the boundary between production equipment and extreme engineering. Its documented failures, track frame cracks, brake fade events, field adaptations, are the record of a machine operating at the absolute limit of what steel can sustain. The D575A-3 SD has been at rest for over a decade. The largest production bulldozer ever built, proven on American mine benches and retired on its own terms. If this story moved you, please like and subscribe. Your support helps us preserve these machines and the histories behind them. Tell us in the comments where you're watching from.